Okay, good afternoon and welcome again to the European and Associative Algebra Seminar. It's a pleasure to introduce the speaker of today, Isabel Martin-Lyons, who will talk about Skew bracoids. Please.
Thank you for the introduction and for the invitation to speak tonight. So yes, I'm going to talk about skew bracoids, which are a fairly novel algebraic object. And the way I'm going to sort of run the talk, first I'll give the definition and sort of talk about these objects a bit in their own right. Then we'll sort of investigate how they relate to more well-established things in the literature. So the skew brace, Hopf-Galois theory, and solutions to the Yang-Baxter equation kind of via semi-braces. Okay, so we'll start with the definition. So a skew bracoid is a quintuple G circle N plus circle dot, where G with circle and N with plus are groups, and circle dot is a transitive action of G on N satisfying this relation here. So G circle dot eta plus mu is G circle dot eta minus G circle dot the identity in N plus G circle dot mu. So this is for all G in G and all eta and mu in N. So we refer to this relation as the skew bracoid relation. G with circle as the acting or multiplicative group, N with plus as the additive group, though we do not assume that plus is abelian, and we won't always write this sort of group operation additively. We will, however, frequently write just the double Gn for this quintuple, and often will suppress especially the multiplicative operation. Okay, so some examples. If you take any group G with circle, then you have two skew bracoids for free. So G with circle, and circle, and G with circle, G circle op, circle. So we have the circles acting as the multiplicative operation in both cases, the additive operation being the circle again or circle op, and then the action as circle and circle. One of the existing objects I mentioned was the skew brace. So this is a triple, G with plus and circle, where G is a group with respect to both plus and circle. And this relationship has to be satisfied. So G with circle of H plus H prime equals G circle H minus G plus G circle H prime. So you can see how this relates to the relationship on the previous slide, but we don't have to worry about sort of projecting into the additive group because we're in the same underlying set in a skew brace. So for any skew brace G plus circle, this can be thought of as a skew bracoid if we just add in a bit of superfluous notation. If we have this action that's really the multiplicative operation. It's something a bit more concrete. If we have D and N natural numbers such that D divides N, we take N to be cyclic of order D and name its generator eta, and G be dihedral of cardinality 2n. We write R for the order N generator and S for the order 2 generator. Then we get a skew bracoid using this action. So we set R to the I, S to the J, acting on eta to the K to be eta to the I plus minus 1 to the JK. So in this skew bracoid, the action somehow mimics the multiplicative operation. This isn't always the case, but this is quite, I think it's quite a nice family of examples and we can do a fair amount with it. Okay, so the title of this section, we included the gamma function. So what is it? So if we take any old skew bracoid, we can define a map from the multiplicative group G circle into the permutations of the additive group N plus. So we define this by gamma sub G of eta is minus G acting on the identity plus G acting on eta. So this is sort of the second two terms in our sort of distribution relation. So it turns out that this gamma is in fact a homomorphism, and it has image in the automorphisms of n plus. And we call this the gamma function of the skew bracoid. Okay. So if we're actually in a skew brace, then it doesn't take long to see that gamma sub G with this definition in the skew bracoid formulation boils down to the one intrinsic to the skew brace, the standard gamma function of the skew brace. And in our dihedral cyclic family, we have gamma sub r to the I s to the j of eta to the k. Then plugging this in and again using multiplicative notation instead of additive. This boils down to eta to the minus 1 to the jk. So this power of r has had no effect on our power of eta, and the power of s has inverted that the power of eta we started with. Okay, so using this we can sort of link skew bracoids to surjective one cocycles. So if we have if we let pi be the map taking G to G acting on the identity, so with a sort of projection, then as by definition this action is transitive, this pi is a surjection, and then pi of G plus gamma sub G pi of H, just subbing in the definitions, and we get these first two cancelling, and we end up with pi of GH. And this means that pi is then a surjective one cocycle for the action of G on N by automorphisms via gamma. Kind of conversely, if we have G and N groups, a homomorphism from G into the automorphisms of N, and a surjective one cocycle pi from G to N, we can define an action of G on N using this surjective one cocycle and this homomorphism, and using this action G and N becomes a skew bracoid. Okay. The other thing we can do with the gamma function is sort of translate our skew bracoid into a subgroup of the holomorph. But first, if we have a group N with plus, its holomorph is the semi-direct product of itself with its automorphisms. There are a few formulations of the holomorph, but this is the one I'll use. So if we take a transitive subgroup of this holomorph, then there's a very natural action of subgroups of the holomorph on the group of which they were made, which goes like eta alpha acting on mu is eta plus alpha mu. So this eta was in N, the alpha was an automorphism, and mu is in N. And using this action, A and N forms a skew bracoid. And conversely, if we have a skew bracoid Gn, we can map G into the holomorph like so. So G maps to G acting on the identity in N, gamma sub G. So this, as we've said, gamma G is an automorphism of N, and G acting on the identity in N is certainly an element of N. The image of this is then transitive, and transitive on N using the same action. And the image of this is then isomorphic to the quotient of G by the kernel of the original action. So for example, in our dihedral cyclic thing, if we write iota for inversion in N, then r to the I s to the j, while acting on the identity, the power of s, the j would flip any power, but if we're starting with the identity, that's still 0. And we just add on the power of r. So this gives us eta to the I. And then the gamma function, remember the power of R had no effect, and the power of S inverted the sign, so inverted the power, sorry. So R to the I, S to the J maps to eta to the I, iota to the J. Hence, the image of G in the holomorph is N, the whole group, semi-direct inversion. And this is isomorphic to G itself precisely when the divisor we chose here is equal to N. So it's kind of as big as possible somehow. Okay, so yeah, now we're going to see the skew bracoid as kind of a generalized quotient of a skew brace. So if we're going to talk about quotients, we need to talk about ideals. So given a skew brace G with plus and circle, recall that the gamma function of the skew brace, it goes like this. Then if we have a skew brace and a subgroup, an additive subgroup, if you like, so a subgroup of G with plus, this is a left ideal if it is closed under the gamma function for all little g and g. And this gives for free that I is also a subgroup of the additive group and that cosets agree in some sense. To be a strong left ideal, we want to be additionally normal in the additive structure, and it's a full-blown ideal if it's also normal in the multiplicative structure. So to be an ideal of a skew brace, you need to be closed under the gamma function, normal in the additive structure, and normal in the multiplicative structure. So as one would expect, if you want to quotient by something, you take an ideal. And since cosets agree, you can just quotient in the group sense with respect to either structure and recover a skew brace. But we're going to try doing something silly and not quotienting by an ideal. So instead, we take our skew brace and a strong left ideal. So it's closed under the gamma function and it's normal in the additive structure. Recall that I is normal in G with respect to plus, so the quotient G by I makes sense as a group with plus. We can also think of this quotient group as a circle coset space, remember cosets agreed, and let G act transitively on G by I by left translation of cosets. Writing circle dot for this action, we can recover the skew bracoid relation via the skew brace relation, sort of using the fact that cosets agree and various things, so that G with circle G by I with plus and circle dot is a skew bracoid. So in our example, this can be seen as such a quotient. So if we take G to be dihedral, we can define a second binary operation on G, just letting those our generators commute. So the R to the I, S to the J dot R to the K, S to the L is R to the I plus K, S to the J plus L. Then this is a skew brace, and the gamma function is given like this. So gamma of R to the I, S to the J of R to the K, S to the L is R to the minus 1 to the J, K, S to the L. Okay, now to actually see our family as sort of our additive quotients of these, we let D be some divisor of N and set I to be the subgroup generated by R to the D, S. Then I is a strong left ideal of this skew bracoid, so it's the additive structure is abelian in this case, so we get the sort of normality for free. And you'll see that the gamma function sort of leaves the power of S alone, and the power of R is only ever inverted. So we can't leave the subgroup, if you like. This means it's a strong left ideal. And then G by I, which is generated by the coset Ri, is cyclic of order D. And if you sort of inspect the action we get, just using left translation of cosets, we see our familiar skew bracoid. Okay, Now, a natural question, having seen this, is do all skew bracoids arise as the quotient of a skew brace by a strong left ideal? The answer is no. So thanks to Bayet, we have an example of a skew bracoid like this, for which the only sort of additional additive operation on G to give G with plus and circle a skew brace has G with plus simple. This means that there can be no strong left ideals to quotient by, so the skew brace cannot directly arise as a quotient as outlined. Okay, so now we move on to Hopf-Galois theory, and to do that we need to explain what that is. So the setting is if we have E over K, a finite Galois extension of fields, and L some intermediate field. This means, of course, that L over K is separable, but not necessarily Galois. We write G with circle for the Galois group of E down to K, and S for the Galois group of E over L. A Hopf-Galois structure on L over K is a K-Hopf algebra H, together with an action star of H on L, such that L is a H modular algebra, and the map J from L tensor H to the K endomorphisms of L, given by J of X tensor H, is the map taking Y to X H star Y, if this map is also an automorphism. Okay, so to hopefully contextualize this a bit, the kind of prototypical example of a Hopf-Galois structure is the classical structure. So if we now focus on the bigger extension, the Galois extension, and don't worry about L, we can take the group algebra KG. This is, of course, a K algebra, and it can be endowed with co-multiplication, co-unit, and co-inverse in a fairly intuitive way. For example, the co-unit is sort of induced by just taking our any element of the Galois group and sending it to 1 in K. This makes KG a K-Hopf algebra. Then E is a KG module with the action defined like this. So a generic element of KG starred with an element of E, and this is just the sum of X sub G and then G of Y. So G is an element of the Galois group, so you can certainly apply that to an element of the field G. E, sorry. Then finally, this map, kind of coming from this action, is an isomorphism of K vector spaces by linear independence of characters. Yes. So a brief history of Hopf-Galois theory for me. So Chase and Sweedler in the late 60s introduced the study of Hopf-Galois theory with a view to inseparable extensions of fields and ramified extensions of rings. And this didn't turn out to bear much fruit, as I understand it. But in the late 80s, Greiter and Paraigis characterized Hopf-Galois structures on finite separable extensions of fields using certain subgroups of this permutation group. So this G is the Galois group from the Galois closure down to our base field, and S was the one from E over L, sorry. Then in 96, following an observation by Childs, Bayet gave a further correspondence between this permutation setting and the holomorph. So this is really made any sort of study of these things more possible, in a sense, because you're working essentially with groups here, permutation groups, and now subgroups of the holomorph, which is much smaller. So it's really tractable. Then in 2016, much more recently, Bachelet sets out a correspondence between braces and subgroups of the holomorph and notes its relevance to Hopf-Galois theory. Then Guanieri and Vendramin in 2018, following the definition of skew braces in 2017, make the connection between Hopf-Galois structures on Galois extensions and skew braces via their mutual connection to regular subgroups of the holomorph. And much more recently, Stefanello and Trapaniers realign the correspondence, making it a bijection and giving more qualitative results. So these sort of last 3 bullet points are all working with braces and then skew braces. And it's kind of this work that we've generalized to the separable and skew bracoid case. So that's what I'm going to discuss now. But first, we note that any skew bracoid G with N can be written with a kind of coset formulation. So if we set S to be the stabilizer under G of the additive identity, then we have a bijection between S cosets and elements of the additive group, like so. So G, S corresponding with G acting on the identity. And if we take a different representative of the same coset, this is going to give the same element of N, because the cosets are precisely differ by elements of the stabilizer. And we can use this bijection to transport the operation in N onto the coset space G by S. And notice that if we do it in this way, the identity coset is then the identity of this group. And if we also transfer the action of G on N onto this coset space, it becomes simply left translation of cosets via the operation in G. Okay, so with that, we get this nice correspondence. So we have a bijective correspondence between Hopf-Galois structures on L over K using our existing notation, and operations plus, such that G circle G by S plus circle dot forms a skew bracoid with the identity coset being the identity of the group, and where the action is left translation of cosets via circle. So how does this actually work? Well, to give a slight flavor of it, explicitly, the Hopf-Galois structure coming from the skew bracoid is this group algebra kind of fixed by G via Galois descent. So what is the fixing by? Well, G acts on E by Galois automorphisms, and it acts on this group via the gamma function of the skew bracoid. So this gamma function really turns up everywhere. And then we can define the action on L given thusly in a kind of natural way. And it's worth mentioning that this is well defined. We can act by this coset on T because T lives in L. So the differing things differ in the way that doesn't matter. Let's say. Okay, and now just to highlight how things are connected. So we have the multiplicative group of the skew bracoid showing up as the Galois group of our larger extension and the thing we fix by in our Hopf-Galois structure. And the additive group on this coset shows up as the so-called type of the Hopf-Galois structure, and is of course related to the Galois group of E down to L. Okay. So one of the central questions of Hopf-Galois theory, and one of the sort of questions we hope to tackle with skew bracoid, so we haven't quite got there yet, is that of the Hopf-Galois correspondence. So if we have H, a Hopf-Galois structure on L over K, for any K Hopf subalgebra H prime, we can define a fix of that structure. So the fix of H prime, i.e. L fixed by H prime, is well, what you would expect. The x's in L for which H star x is the co-unit applied to hx, these things should be equal. Then this fixed map is necessarily injective and inclusion reversing. So this isn't quite as good as what you have in the classical Galois setting, where of course it's bijective and inclusion reversing. So the question is, when is it also surjective? Well, to tackle this, we can look at some substructures. So just to remind you a bit of how ideals work in a skew brace. So we have this kind of a subgroup of the additive group, and then we have three tiers. So we have the one where it's closed under the gamma function, normal in the additive group, and then normal in the multiplicative group. And to kind of give some intuition for the definition in the skew bracoid, recall that it was the strong left ideal that we quotiented by to get a skew bracoid. So if we started with a skew brace and we want a skew bracoid, we only really need a strong left ideal. So with that said, and I'm sort of focusing on this coset setting just to make it a bit easier. If we let the skew bracoid G by S, if we take that and a subgroup G prime of G containing S, we say that G prime acting on the identity, the additive identity, is a left ideal if it's closed under the gamma function, and an ideal if kind of the image of its projection is additionally normal in the additive group. Okay. Then theorem, a Hopf-Galois structure corresponding to a skew bracoid. So we have E G by S fixed by G corresponding to a skew bracoid G by S. We take G prime as above so that L fixed by G prime in the Galois sense is an intermediate field of L over K. So taking all G primes like this should recover all the intermediate fields by classical Galois theory. Then this fixed field occurs in the image of the Hopf-Galois correspondence for this Hopf-Galois structure if and only if G prime acting on the identity is a left ideal of our skew bracoid, and we can form a quotient structure G fixed by GL over K if and only if it's a full-blown ideal. So it's normal in the additive group. So we can work through this for our example. So every subgroup G prime of G dihedral containing S, so S should be the subgroup, should be the stabilizer of the identity in the additive group. So here it turns out to be R to the DS. Any subgroup of G containing S is of the form generated by R to the Fs for some F dividing D. Then what does this look like once we've put it in the additive group? Well, G prime acting on the identity is the set of R to the IFS. Then we look at the gamma function. So gamma sub R to the I, S to the J of elements in our set of interest is R to the -1 to the J KF S. And this is certainly in our set. So this is closed under the gamma function. And given this, we have a result saying this makes it a subgroup of the additive group, but you can also just see that sort of by inspection. Hence, G fixed by L fixed by G prime occurs in the image of the Hopf-Galois correspondence for the Hopf-Galois structure E G by S G for all G prime. So it doesn't matter which divisor F we picked, all G prime will work. So the Hopf-Galois correspondence is surjective in this case. And since our additive group is abelian, each of these is additionally normal, so we can always form a quotient Hopf-Galois structure for every G prime. Okay. Now, finally, we're going to, well, sort of finally, we're going to move to solutions to the Yang-Baxter equation via semi-braces. Okay. But what is a semi-brace? A semi-brace is a triple G with plus and circle, where G with plus is a group, and where G with circle is a group, and G with plus is not quite a group. It's a left-cancellative semigroup. And we want these two to interact like this. So G circle H plus H prime equals G circle H, G circle G inverted with respect to circle plus H prime. Okay, so some examples. All skew braces are semi-braces. And it may not be initially obvious, but if you apply the skew brace relation to this second term on the right hand side, then this G cancels with this G inverse, and you end up with the sort of traditional skew brace relation, which is satisfied in the skew brace, therefore this must be satisfied too. More concretely, if you take G with circle to be dihedral, as I seem to like to do, and define an additive operation like this, so R to the I, S to the J plus R to the K, S to the L equals R to the I plus K, S to the L, then G with plus and circle is a semi-brace. So you can see that this additive operation, it's not quite a group operation, but it's good enough, and we have the left cancellativeness. Okay. So some facts about semi-braces. So if we let G with plus and circle be a semi-brace, write E for the set of additive idempotents, then the multiplicative identity little e is in big E. E is a subgroup of G under the multiplicative operation, and E with plus and circle is also a semi-brace. So this is kind of, the additive operation is only idempotents for this semi-brace. And then G plus little e is a group under both plus and circle. This kind of, we can call this the group part of the additive operation. And then G plus E with plus and circle is a skew brace, a real skew brace. And finally, G with plus emits a decomposition, G plus E plus E. So these kind of facts about semi-braces tell us a bit about the family of skew bracoids, which we're going to be concerned with, because it's not, we can't yet connect all skew bracoids with solutions or indeed with semi-braces. So which skew bracoids can we connect? So we say a skew bracoid G with N contains a brace if this stabilizer has a complement H in G, so that G has an exact factorization HS. This condition is equivalent to just the existence in the abstract of a subgroup H of G which acts regularly on N. This means that H with N is a skew bracoid in which the stabilizer of the identity is trivial. Then we have that the stabilizer with the identity is a skew bracoid with a kind of, obviously the action isn't really doing anything, it's kind of trivial in some sense. And H with N is essentially a skew brace, because we have this regular action. This means that H moving to H acting on the identity is a bijection, and we can use this to transfer the group structure in one group onto the other to get a bona fide skew brace. So this is kind of similar to the idea with the coset, but slightly more general. Okay, so obviously we're are we? We seem to be specifying somewhat from skew bracoids at large, but how strong is this condition? Do all skew bracoids satisfy it? Well, if we view this from the holomorph, we're asking for our transitive subgroup to contain a regular subgroup. And intuitively, this feels common, though we do have examples from that setting that show it's not true in general. So not all skew bracoids contain a brace. So if we look at our dihedral cyclic example, remember this had image the additive group semi-direct inversion in the holomorph. This always has a regular subgroup, just the whole group and itself, so the subgroup generated by eta. And if D is even, we could also take eta squared, with the subgroup generated by eta squared, eta iota. If we allow non-trivial kernel of the action, so we haven't passed to the holomorph and we don't have a trivial kernel anyway, then we get a lot more counterexamples. So in this family, if D and n over D are not co-prime, and the GCD of D and 2n over D is greater than 2, then our stabilizer does not have a complement in G, which means these skew bracoids do not contain a brace. Okay, but let's actually connect the dots. So if we have G with circle a group with an exact factorization HS and identity E, then there is a bijection between binary operations plus and transitive actions circle dot of G on H such that G circle H plus circle dot is a skew bracoid with S equal to the stabilizer of the identity in this skew bracoid. So this S has to line up with this S in our exact factorization. So a bijection between this and binary operations plus hat, for which G plus hat circle is a semi-brace with S, the set of additive idempotent, E is what I've been calling it, and G plus hat E equal to H. So group part H and idempotent S. So the kind of main ideas of the root, let's say. If we start with the skew bracoid and we want a semi-brace, we define the plus hat to be G1 plus hat G2 equals G2 gamma sub G2 inverse of G1 acting on the identity. So this G1 acting on the identity is to force the argument into our additive group so that we can apply the gamma function. Yes, and then from semi-brace to skew bracoid, we define the additive operation in H to just be the opposite of what it was in the semi-brace. You'll notice that this is a bit simpler, but this is going from semi-brace to skew bracoid, we only care about the additive operation on H, whereas from skew bracoid to semi-brace, we're trying to put an additive operation on the whole of G. So that's why this way is a bit more complicated. And what should the action be? Well, G acting on H is G circle H plus E. So we just do the additive, the multiplicative operation from the semi-brace and then project into the group part, which is H. Okay, now I promised that this would relate to the Yang-Baxter equation. So first off, what is the Yang-Baxter equation? Well, a solution to the set theoretic Yang-Baxter equation, which I'll now just call a solution, is a non-empty set G together with a map R from G cross G to G cross G, satisfying this sort of braid relation. So on the left-hand side, we apply R to the first two components and the identity to the third, then apply R to the second two components and identity to the first, and then apply R to the first two components and identity to the third, and sort of similarly but kind of mirrored on the right hand side. And these should be equal as functions on G cross G cross G. Then given a solution R on G, for all x, y, and g, we write R of xy equals lambda sub x of y, rho sub y of x. So this gives us a family of maps, lambda sub x from G to G, a family of maps, rho sub y from G to G. And this allows us to add to the terminology a bit. So let's do that. So suppose G with R is a solution, and write R in the way we've just done with the lambdas and rhos. We say that a solution is bijective if R is bijective. Left non-degenerate if lambda sub x is bijective for all x in G. Right non-degenerate if rho sub y is bijective for all y in G. And non-degenerate if it's both left and right non-degenerate. Then the trivial solution, kind of unintuitively, so R taking xy to xy is clearly bijective, but it's degenerate. So lambda sub x of y is always x, meaning it's, well, very rarely bijective. So this is degenerate. But the choice solution, which takes xy to yx, is bijective and non-degenerate. Okay. So how can we get a solution from a skew bracoid? And this sort of can be seen via semi-braces, but I think it's worthwhile to do it directly. So if we have a skew bracoid G with N that contains a brace, so H is our complement to the stabilizer. We have, as I said, a map taking little h to H acting on the identity, and this should be a bijection between H and N. We can write B for its inverse. So B of eta is the unique element of H that, when acting on the identity, gives eta. With this, we define lambda sub x of y to be B gamma sub x of y acting on the identity. So again, we have this y acting on the identity to force the argument into H. And this B at the end to kind of pull back into H, but as part of the multiplicative group. And then from this, we define rho sub y of x to be lambda sub x of y inverse. This is with respect to the multiplicative operation, xy for all xy in G. Then this lambda and rho form a Liu-Yanzu pair, so that the solution kind of built from these forms a right non-degenerate but possibly left degenerate solution. So this is left degenerate in all cases where you didn't basically have a skew brace to start with. Okay, so for example, if we take our dihedral one, but we pick D to be N, so this one is actually isomorphic to its image in the holomorph. Then the stabilizer of the identity is just the subgroup generated by S. And this, of course, has the complement R generated by little r. So then plug in generic elements into our formula. R to the k, S to the L acting on the identity is just eta to the k. The power of S would invert the sign, and we just add on the power of R. Then we apply the gamma function. So remember, the power of R has no effect, and the power of S inverts. So this is B of eta to the -1 to the j k. And then we apply B, so which element of our subgroup generated by R can we act by to get this power of eta? Well, it's simply R to the -1 to the jk. Then we plug the inverse of this into our rho formula, and this boils down to rho of R to the k, S to the L of R to the I, S to the j is R to the I, S to the j plus L. Hence, if we take G and the map sending R to the I, S to the j, R to the k, S to the L to R to the -1 to the jk, R to the I, S to the j plus L, this pair is a solution. Okay, but alternatively, I mentioned sort of in the holomorph formulation that there was another regular subgroup at play. So if we take n to be even, we can also use this complement generated by r squared rs. And running that through, I won't bore you with the details, we get that this is also a solution, and you can see hopefully that it is kind of different in a meaningful way. So if nothing else, the first component, we dispense with our power of s, and that's going to sort of stay gone, if you like, whereas in this solution, the power of s remains present. So that's basically all I had to say, but I'll finish with a few open questions. So kind of one for the abstract, it would be nice to have some notions of products of skew bracoids. So we've got kind of a lot of connections to other areas of study, as you've seen, but it's a very new object, so we haven't got a lot in and of itself. So we have this idea of an induced skew bracoid. This kind of comes from Hopf-Galois theory, and kind of to give you some sense of it, if we have a skew bracoid, we can kind of reduce the stabilizer, if you like. But we only have a few vague ideas of what a semi-direct product or a match product should entail. Then Stefanello and Chapliniers use skew bracoids to great success in the study of the Hopf-Galois correspondence. In the Galois case, as I said, it would be nice to use skew bracoids in a similar way. And finally, we've made this connection between skew bracoids and solutions, but is that actually of use to anyone? I think it's kind of cool that you can draw multiple solutions from a single skew bracoid, but that does mean that sort of any hope of bijections is going to be a bit tricky. And on the other hand, we've kind of, via skew bracoids, we've connected semi-braces to Hopf-Galois theory. This is new. Can semi-braces be made use of in Hopf-Galois theory at all? And that's all.
Thanks, Isabel, for your nice and interesting talk. And are there any questions? Please.
Yes, I have a question. Thank you for your nice talk. What about representation theory for skew braces or skew bracoids? Does it make sense in some way?
I have a kind of vague answer there. Skew braces there has been kind of developed, I think, some representation theory. There's a paper, I think, of Vendramin, and more recently on the archive something by Cindy Sang, but I can't give you any details, and definitely nothing for skew bracoids yet.
Okay, thank you.
Other questions? Comments or remarks? Okay, if not, let's thank the speaker again. And we will resume as usual next Monday at the usual time. Goodbye. Bye-bye.